Hi, I'm Yanis Katsis from IBM Research Almaden, and in this part of the tutorial, I will be talking about the work that has been done in table understanding. To start off, let's take a step back and let's look at the bigger picture. So far, we have talked about table extraction, which is the task of identifying the tables that appear within a document together with their structure. While table extraction is crucial to get information out of documents such as PDFs, images, etc., if you think about the output of table extraction, it's pretty structural. It's mostly information about how different cells are aligned with each other to form a grid. If we want to successfully do any table processing, for instance, to create a knowledge base or to answer questions, then we will have to go a step beyond and understand the semantics of the data appearing within tables. For instance, in this table, we will have to understand that 3,476 is not a standalone value. Instead, it corresponds to the passenger operating revenues for the third quarter of 2014. In this tutorial, we will refer to all the work that has been done in identifying these semantic annotations of cells and tables collectively as table understanding. These cell annotations can then be passed to downstream applications to, for instance, create knowledge bases, answer questions, etc. At this point, you're probably asking, but what do we mean by semantic informations and what do we mean by semantics of tabular data? I think this is best illustrated through an example. And for this, I will need your participation. Let's look at this table, which is a financial statement of Air Canada. And let's focus on the blue cell, the one that contains the $sign and the value 13 within parentheses. Now, let's assume that I cannot look at the table and you're trying to describe to me what this cell represents. You're trying to describe it to me in natural language. What would be the sentence that you would come up with? Let me pause here for a few seconds so that you have time to take a deeper look. Thank you for your participation. Now let's look at one particular interpretation of this cell. This says that 13 is the unaudited comprehensive net loss of Air Canada in the 6 months ended June 30th of 2015. And it is actually not 13, it's 13 million Canadian dollars. Let's now try to reverse engineer how we came up with this explanation. It should be obvious that in order to come up with this explanation, we brought together semantic information about the cells from different places. Let's use color coding to make it more obvious. For instance, comprehensive net loss is coming from what we will call the row headers corresponding to this cell. The time period, 6 months ended June 30th of 2015, is derived from the column headers. Then the information about the currency, Canadian dollars, the scale that we're talking in millions, and the fact that we're talking about unaudited values is coming from information on the top left corner of the table. And finally, Air Canada, the fact that we're talking about Air Canada, this information does not even appear within the table. This is coming from the title of the document. Next, we will be talking about all the work that has been done in identifying the semantic information, which we will classify into different types. To make it easier to review existing work, we classify the semantic information based on the location where it appears. First, we will be talking about identifying big table regions that contain information about the columns and the rows of the table, which are commonly called the column headers and the row headers. Then we will present approaches that try to find context that appears in other places within the table, such as the currency and the scale in our example. Then we will proceed to find information that appears in places within the document but outside the table, such as the table and document title. And finally, we will talk about approaches that look for semantic information that may appear outside the document. And a good example of those are approaches that try to link table contents with external knowledge bases. And this reflects also the outline of the table understanding section. Before proceeding though, let me make a quick disclaimer. Here we're trying to make a distinction between two things. On one hand, the enrichment of the table with semantic information that can be useful for different end tasks, which we call table understanding. And on the other hand, solving these end tasks, which we refer to as applications, such as table search, table query, etc. Note though that this is not a standard distinction. For instance, in the literature, we can find works that combine aspects of both. That is, in the context of a very particular application, they may also solve some table understanding subtasks. However, we believe that distinguishing them can be helpful for two main reasons. First, it helps us understand and compare existing works. And second, we hope that it may enable reuse within the community by allowing people that want to work on particular applications understand what are the prior works that they can leverage. Because of that, while we will be briefly talking about applications at the very end of the tutorial, for the second part, we will be mainly focusing on works done in table understanding. Thank you. Let us now talk about the problem of identifying table regions. Tables are in general composed of three main regions: column headers, which describe the contents of the corresponding columns, row headers, which describe the contents of the corresponding rows, and data or body cells that contain the actual data. Also note that both column headers and row headers may include nesting. For instance, 2014 appears nested within 6 months ended June 30th, and net income or loss appears nested within comprehensive income or loss. For now, we will ignore nesting, but we will come back to it later on. In order to identify table regions, multiple different approaches have been proposed. We start with the simplest, which are unsupervised methods. The intuition behind them is that headers look different than data cells. For instance, if we look at this picture, we will see that there is different alignment between column headers and data cells. There is difference in bold information. There is difference in the containment of alphabetic characters, etc. So the idea behind unsupervised methods is that we first extract some features about the rows or columns, and then we feed them into heuristics that try to distinguish between headers, header cells and data cells. A simple example of such an approach is one of the baselines that is presented by Funk et al., which computes the pairwise similarity of consecutive rows and tries to find the local minimum of the similarity, which ideally corresponds to the splitting point between column headers and data rows. Another approach, unsupervised approach, is presented by Seth et al., where they use heuristics that leverage information about repeated cells or empty cells in order to identify what they call stub head, which is intuitively the cells where column headers and row headers overlap, and which can be used to define the three table regions. A natural evolution of unsupervised approaches is approaches that use machine learning methods. So the difference from unsupervised approaches is that now, in addition to features, we also have labels corresponding to column headers, row headers, and data cells, and we feed all of them into some machine learning technique that is then trained to correctly classify the different components of the table. The difference between the approaches that fall under this category is how is the problem defined as a classification problem, which are the machine learning methods that are used, and which are the features that are used. One way to define this as a classification model problem, is to classify entire rows if we're looking at identifying column headers, or entire columns if we were looking at identifying row headers. And this is the approach that is followed, among others, by Fang, Pinto, Adelphio, and more. However, this is not the only approach. For instance, Kochi et al. Look at it as a cell classification problem in which each individual cell is labeled, and then the model is trained to predict the type of each individual cell. And yet another set of techniques model this as a table classification model problem, where entire tables are classified based on their layout. And this is an example of different layouts that can be identified. The first one corresponds to relational tables that have the column headers on the top, which are similar to the ones that we would find in a database. Then we have entity, listing, or key value pair tables, which intuitively are tables that describe the properties of one entity. And they have typically two columns. On the left column, they have the row headers containing the properties. And on the right column, they have cells containing the actual values of the properties. And the typical example of entity tables are typically the info boxes that we can see in Wikipedia. And then we have matrix tables that have both column headers on the top and row headers on the left. Now, it is interesting to note that the table class implies the header structure. However, this may not solve completely the header identification problem, because, for instance, for relational tables, we may still need a header identification algorithm to decide whether a column header exists, and if it exists, how many rows of column headers we have. However, since this approach finds the layout of the tables, we think that it falls within the table region identification problem. It is also interesting to note that this way of modeling the problem as table classification, this has not always been used for classifying tables based on their layouts. Actually, if we look at it historically, first, researchers used table classification in order to distinguish between tables that are what they were calling genuine tables, so tables that contain data, versus non-genuine tables, that is, tables which use, for instance, table tags when we look at them in HTML documents, but they may not contain data, but instead be used for navigational purposes or to display calendars, etc. But as time went on, these techniques were more and more used to identify the layout of tables. Actually, also in terms of techniques, there are different machine learning algorithms that naturally were used. But an interesting observation there is that judging from papers that compared multiple machine learning algorithms, random forest usually was performing among the best. Also, in terms of features, each work used different sets of features, but the features in general fell within a few broad categories. And in particular, some of them were layout features that had to do with the structure of the table, including how many cells are in a table or how many rows or columns are in a table. Others were lexical features, which look at the text that appears within cells, and they try to capture whether certain character classes were present, such as numbers, alphabetic characters, special punctuation characters, etc. And then the third broad list of features has to do with formatting information or HTML features, the font styling, the font size, coloring, etc. Also, it's important to note that depending on how one defines the features, it's very easy to end up with a pretty large number of features. For instance, in Eberus et al., they are using 127 features, but this has to additionally be addressed through feature selection methods. The natural evolution of these techniques is to apply deep learning algorithms to the same problem. And here we will present two recent proposals of deep learning models that were both presented by Nishida et al. The first one is an extension of the hierarchical attention networks that has been proposed initially by the NLP community to help in document classification. The main idea is that documents are hierarchical in nature, since they are composed by sentences, which in turn are composed by words. Therefore, the hierarchical attention network simulates this structure and has two layers. The first one attends to words, and the second one attends to sentences. Nishida et al. Extended this to tables by creating three layers: tokens, which are used to form cells, and cells, which are used to form either rows or columns. And depending on whether rows or columns were used for the second layer, for the third layer, this led to either a row directional or a column directional network, which they then combined into a bidirectional network. In addition to this approach, they also presented an alternative deep learning architecture, which is composed by a combination of an RNN model and a CNN model. The intuition behind it is the following. If we look at the deep learning literature, we can see that RNN models have traditionally worked well for text, while CNN models have traditionally been used in image processing. So if we look at tables, if we look within a cell, we will see that it is composed of text. However, if we look at the entire table and squint a little bit, we will see that it starts looking like an image. Based on this intuition, they used an RNN, and in particular an LSTM, to capture the semantic representation of each cell, and then they feed the output into a CNN, which captures the relationship between the individual cells. And this concludes this historical evolution of approaches that have looked at table origin detection. But one thing that we did not cover, and we referred to it in the beginning, is hierarchies. We already said that both column headers and row headers can include nesting. For instance, here 2014 is nested within 6 months ended June 30th, and similarly for these row headers. Now, arguably, the column header hierarchies are pretty straightforward to recognize because they are implied by the structure of the table. If a column header appears under another column header, then it is conceptually nested within it. But for row headers, we cannot say the same because all row headers appear within the same column. So the structure of the table itself does not help us identify which row header is nested under what row header. So in order to go from this representation to this implied row header hierarchy, we will need more sophisticated methods. In the literature, we have seen several approaches for hierarchical row header detection. In this tutorial, we will just briefly present two representative ones. An interesting approach presented by Chen et al. Is based on the idea of representing the hierarchy as a graphical model where each variable corresponds to a candidate parent-child pair. However, a potential drawback of looking at pairs of row headers to decide whether they form a parent-child relationship is that this process utilizes only local information. So it may miss more global information about what is happening in the rest of the row headers in order to correctly identify the row header hierarchy. To address this issue, a follow-up work by Chen et al. Looked at this problem as a rectangle mining problem. The main idea is to identify what the authors call interesting rectangles, which conceptually are rectangular regions that contain all descendants of a particular row header. And this approach iteratively combines smaller rectangles into bigger ones based on their similarity until it forms and identifies the final row header hierarchy for the entire column. And with this, let's conclude our brief overview of the related work in table region detection. Thank you. So far, we have looked at the problem of identifying table regions, which allow us to find the column headers and row headers of each cell. However, as we explained towards the beginning of the table understanding section, there is more semantic information about cells to be found beyond row and column headers. Also, as we explained, this information appears in different places. It may appear within the table, it may appear within the surrounding document, or it may appear even outside the document. So let us, in the rest of the table understanding section, go through each of these classes of semantic information, and for each of them, explain both the problem definition and the work that has been done in the respective area. Let's begin with identifying context that appears within the table beyond column headers and row headers. The first important thing to note here is that this semantic information may have different types. Going back to our example, we can see that, for instance, here we have information about currency that appears in the data cells. We have information about both currency and scale, the fact that we're talking about millions in the top left corner of the table. And we also have information that this is unaudited data, which also comes from the left top corner of the table. So the first important thing is we have information of different data types. And the second is that this information may have also different scope. And let me explain what I mean by scope. Let's take as example this cell at the top left corner, which contains information about both currency and scale. Even though it appears in the top left corner of the table, semantically, it applies to all the data cells because it describes that all of these values are actually Canadian dollars in millions. However, if we look at this dollar sign that appears within a data cell, then the standard writing convention means that this should be applied only to a subset of the data cells, usually the data cells that appear beneath it up until the next currency symbol. So we have to solve two sub-problems here. First, identify the semantic information and these different types of semantic information. And for each of them, identify their scope and propagate them to the corresponding data cells. Looking at the literature, it appears that this problem usually does not appear as standalone work. Instead, it often appears as a smaller intermediate step within broader work. And the second comment is that it often appears to be very domain specific. So the solutions are for specific domains. As an example, let's look at this table, which was taken by a paper by Kim et al. On a very different problem. The paper is about linking text and tables, and we will actually look further into it later on. But while they were trying to solve the general problem, they had one step in which they were identifying scales, which they call orders of magnitude. They identified them in column headers and propagated them down to all the data cells within the respective columns. So this is one example of how this problem is hidden within broader work and how it is domain specific. For instance, in this case, they were interested in orders of magnitude or scales, and that's why they were looking for very particular values such as millions, billions, etc. So unless we missed something during the literature review, I think this is an area that could benefit from additional work in two different ways. One is recognizing it as a problem that is important in its own and which can help many downstream applications. That's one. And the second is trying to do some work that solves this problem, not for a very particular domain, but in a more domain agnostic way. With that, let's move to the next part, which is about identifying context that may not appear within a table, but appears instead within the surrounding document. Going back to our example, this, for instance, would correspond to identifying the table title or the document title. The main idea here is that the surrounding text often contains very important information about the table and the cell. And this information should ideally be extracted and associated with the respective table contents in order to enable downstream applications. For instance, both table question answering and table search could benefit from contextual information such as the table caption or the document title. In this thread, we categorize the existing work in two big buckets. One has to do with what we call shallow context extraction. This is mostly about extracting simple metadata about the table or the document. The second is approaches that require a deeper semantic understanding of both the table contents and the text. And here we will see two examples. One is about linking table to the surrounding text, and another is about leveraging the text to generate more informative table titles. This is an example of shallow context extraction for tables. And here we see that this approach identifies different types of metadata for the table and the document, including the document title, the document authors, table caption, page information, etc. Please note that depending on the domain and the document format, this information may be or may not be there. And also, again, depending on the document format, it may be easier or harder to extract it. For instance, if we look at scientific publications, we're doing a pretty good job at adding captions to our tables. And also, LaTeX is doing a pretty good job at formatting them in a uniform way, which makes it easier to extract them. On the other hand, if we look at other domains, for instance, if we look at business documents, table captions may not be as easy to extract. And in yet other domains, for instance, looking at web tables, a table caption may not even appear. So this is something to keep in mind regarding the complexity of this problem. Now, moving on to approaches that require a deeper semantic understanding of text and tables, let's first look at an approach that tries to link the text with the corresponding table cells. On the left, you can see a figure that is taken from this work by Kim et al. And you can see on the top, highlighted in yellow, a sentence, and below you can see the corresponding tables, and also highlighted in yellow, the corresponding cells, which are referred to by the sentence. Let's actually go through the example to make it clearer. Reading the sentence, it says, men said slightly more than women that it would be very hard for them to give up computer, the internet, and PDAs. Now, if we look at the table, we see that this sentence refers to computer, internet, PDA, and the corresponding statistics for both women and men, and that's why these cells are all highlighted in yellow. In order to do this linking between text and cell contents, the authors of this paper use an approach that first identifies the headers and then uses different strategies to match the sentence to the table cells. The first strategy has to do with identifying words in the sentence that appear in unique cells. And the intuition here is that if a word appears only in one cell, it's a pretty strong clue about this cell being the relevant cell for the particular sentence. Then they utilize a syntactic analysis of the sentence to understand the hierarchical structure of the text and try to find structural subcomponents, for instance, the subphrase dial-up connections, that then they try to match to the table cells. And finally, they go beyond syntactic analysis and they try to do semantic analysis by using word2vec. This allows them to match phrases that may look very different from each other, but they're talking about the same thing. For instance, phrases such as discuss issues, which is semantically equivalent to talking about topics. And finally, being a pragmatic approach, it also employs rules to further refine the matches. Now, let's move to a different work within the same space of identifying table context within the document. Here, we're looking at a different problem. We're looking at web tables, and we're trying to generate table titles for them. The problem is that web tables often lack titles, or when they have titles, the titles may not be as informative. For instance, looking at this Wikipedia table, we see that it has a title called television. However, that's not enough to explain what the table contains. Thus, the authors try to leverage the surrounding context to generate more informative table titles. for instance, using their approach, they're able to generate a title that is called Nicole Eggert Television Roles, which is arguably much more informative than simply television. The approach that they take leverages different types of information from the input document, including the page title, the section headers, the column headers, and others. And the model is designed by using a pointer generator network, which was first proposed for abstractive summarization, and combining both a copy and a generator mechanism to both copy existing words from the document, but also generate novel words that may make better and more readable titles. With that, let's wrap up this thread about works related to identifying context that appears within documents. And to add my personal commentary here, I think that it's a very interesting thread. And conceptually, the interest comes from the fact that these works are trying to bridge two very different worlds. On one hand, we have the table data that are by definition more structured. And on the other hand, we have the text data that are by definition unstructured. So it's very interesting to see how these works try to bridge and link structured to unstructured data. Let us now increase our scope even more and look at the problem of identifying context that appears outside the document. The prime example here is linking information that appears within the table to external sources such as external knowledge bases, for instance, Wikipedia. For instance, we can link net income, which appears within the row header, to the corresponding net income concept in Wikipedia. By doing this linking, we are bringing in additional semantic information about the table contents that can subsequently be used and leveraged by multiple downstream applications. For instance, applications that could benefit from that would be applications that try to enrich existing knowledge bases from information coming from tables, or applications that try to integrate information from tables into potentially new knowledge base. In this tutorial, we will not be reviewing the table to knowledge base linking work in detail. For that, we would like to refer you to a great tutorial given by Zhang et al. On the topic in SIGIR 2019. However, we would like to spend at least a few minutes to define the problem. Table to knowledge base linking can be classified into three main subtasks. And the subtasks depend on the type of table component that we're trying to link to the knowledge base. The first one has to do with linking columns by using the knowledge base to identify the type of the column. And this is also why it's commonly referred to as column type identification. For instance, in this example that shows information about tennis players, we would like to use the knowledge base to identify that the player column is of type person. The second subtask has to do with linking cells. And in this case, we're trying to link a cell to the corresponding entity in the knowledge base. And this is why this is also commonly referred to as entity linking. An example for that is recognizing that the mention Rafael Nadal refers to the corresponding Wikipedia entity for the famous tennis player. The next task has to do with linking pairs of columns by using the knowledge base to identify the relationship between them. And this is why this is also referred to as relationship linking or relationship extraction. As an example, we want to use the knowledge base to identify that the years column corresponds to the career years of the players that are mentioned in the player column. Again, For additional information on the related work done in each of these subtasks, please refer to the CGIR tutorial, where you can see detailed information about each of the threads. However, I think one work that definitely deserves a mention here is the influential work by Venetis et al. At recovering semantics of tables on the web. This falls under the same umbrella of linking tables to external information, but instead of using a standard structured knowledge base, they are using information derived from mining text on the web. In order to do that, they follow a two-step process. Let's look, for instance, how they address column type identification. First, they mine the text to create an is-a database. For instance, if they visit a web page that contains the sentence, the conference features 12 workshops, such as the mining data semantics workshop, then they infer that mining data semantics workshop is a workshop. And once they have populated this is-a database, they can use it to identify the types of table columns. For instance, they can identify that in this case, this column contains information about workshops. And they use similar process and techniques for relationship extraction as well. I think this work is important to mention for two reasons. One is because of this creative idea of leveraging text information to find and enrich tables with additional semantics. And the second is because the authors do a great job at motivating the problem, both through the write-up and experiments, the problem of bringing in additional semantic information into a table that can then be leveraged by multiple downstream applications. And this is also exactly what we're trying to do in this tutorial by grouping all the works that have to do with semantic enrichment of table contents under this umbrella of table understanding. And with this, I would like to conclude our short review of work done on table understanding. In the next section, we will be talking about the resources that the community has made available for people that want to work in the area. Thank you. But before concluding the entire section, I wanted to take a few minutes to at least talk about the resources that are available if you want to work in this area. When we're talking about table understanding, two of the first resources that we should mention are two very big web table corpora, the Web Data Commons, the WDC Web Table Corpus, and the Dresden Web Table Corpus. Both of them are large-scale corpora of tables that were crawled from the web, and both of them classify tables into relation, matrix, and entity types, as we have explained earlier, and they also include additional metadata, such as, for instance, page title, table captions, etc. And to get a sense of the scale, they both contain hundreds of millions of tables coming from the web. Personally, I think that this has been a great resource that has enabled a lot of work in the area of web tables, both to understand the structure of web tables, but also to process them and do table understanding tasks. One thing to mention, though, is that these are corpora of web tables. They do not contain ground truth annotations for any particular web understanding task. However, we have news on the annotated dataset front, and they're pretty recent. Actually, in 2019, we have seen the release of DECO, which stands for Dresden Enron Corpus, which contains more than 1,000 business spreadsheet documents together with human-provided annotations for table origin identification. The two main points here is that it contains the human-level provided annotation, so it can be used as a gold standard. And the second is that it contains business documents. And I think that this is a very nice counterpart of the web table corpora, and hopefully this will accelerate the work on processing tables beyond web tables. When we're talking about annotated ground truth data, if we go to the table to knowledge base linking subcommunity, we will also see that there are a few datasets, annotated datasets there. Here you can see a few examples, some smaller than others, but it's important to see their presence. And it's also important to see that this subcommunity has also created challenges. For instance, there is the SEMTAB challenge, which was held in 2019, and it's also being held this year in conjunction with the International Semantic Web Conference. And it includes subtasks for all three linking problems that we have seen. I think the table to link knowledge-based linking subcommunity is a great example of attempts for both sharing and standardizing tasks. With that, let me conclude the table understanding section with a very brief discussion. In this section, we have seen different sub-areas of table understanding. And we have seen that there has been substantial work in some of them, for instance, table origin identification, and to some degree also table to knowledge base linking, but less in others. So I think that there is potential for more work in some of the sub areas, especially identifying context within a table or identifying context within documents. The second has to do with domains. Primarily due to the large web table corpora, there has been a substantial work done on web tables. On the other hand, if we look at scientific and enterprise tables, there are some threads there. So there are threads on identifying tables from spreadsheets, and but this is much more limited than the web table work. Hopefully, with the addition of the DECO dataset and other work that is being done in the area, we can start studying more different domains and understand the differences of tables appearing in different domains and understand the different and unique challenges that they may pose. And as a last point, let's also talk a little bit about resources. We have seen very valuable resources, such as the web table corpora, yet except for table to knowledge base linking and also the DECO dataset, there has been limited amount of annotated data and standardized benchmarks for table understanding tasks. I think here we can definitely learn from different communities, including the table to knowledge base linking subcommunity and the table extraction community, as we have seen before, to work towards increasingly sharing data sets, defining the subtasks, and creating benchmarks. And I think that here we can also potentially get a little bit creative and leverage resources that are created for other tasks or by other communities. For instance, if we talk about table extraction and understanding, can we look at the data sets or the corpora that have been put together for table extraction and try to use them potentially for table understanding tasks? So hopefully this tutorial will help in this regard. And with that, let me conclude the table understanding section. Thank you for listening.